Okay, my name is Paul Asti, and I'm doing the FRQ from 2005, number 5. So the question is, a car is traveling on a straight road. For times 0 to 24 seconds, the car's velocity, v of t, in meters per second, is modeled by the piecewise linear function defined by the graph above. We can see that there. And so A is find the integral from 0 to 24 of v of t dt. Using correct units, explain the meaning of that integral. Okay, so looking at A, we're looking for area under the curve. The definition basically of an integral is what's underneath this curve, and so that's what we're looking for. And the way to do that is actually to split it up into three parts. It's three linear functions is what they tell us at the beginning, like I said. And so we have two triangles and a rectangle. So the area of a triangle is 1/2 base times height, and the area of a rectangle is base times height. So we're just going to plug in numbers pretty much. And so if you look back at the back up here, you see this triangle goes from 0 to 4, the rectangle goes from 4 to 16, and the last triangle goes from 16 to 24. So, and it goes up to 20. So we have 1/2 4 times 20, it's the first triangle. Then 12 times 20, 16 minus 4. And then 1/2 8 times 20, 24 minus 16. And that comes out to 360. And now we're looking for units. It says explain using correct units. And so what I like to think about is this set of graphs that Mr. Corman taught me in physics last semester. And so basically there's three graphs you want to think about. This one is position over time. Here we have velocity over time, which is what we have here. And here we have acceleration over time. And the slopes and areas under the slopes are all closely related. So if you have position over time, the slope is velocity. Velocity over time slope is acceleration. And acceleration over time, the slope is jerk. And the area under the curve for position over time is meaningless. For velocity over time, it's position. And for acceleration over time, it's velocity. So slopes are going forward. Areas under the curve are going backwards in a sense if you think about it like that. So now that we know that it's just the position. We're looking at this one. So 360 meters, they give us that in the 24-second interval. So that's part A. Okay, moving on to part B now. Part B's question is for each of v prime of 4 and v prime of 20, find the value or explain why it does not exist. Indicate units of measure. So let's start out by looking back at our graph. I've drawn another one here. And so here we have v prime of 4 is at that point there where the triangle becomes a rectangle from the last one. And v prime of 20 is right in the middle of the hypotenuse of this other triangle. And so if you remember, Mr. Farrar told us sharp turns, there is no possible differentiation. So we should know already that v prime of 4 does not exist. V prime of 20 obviously does because it's a linear function. And so let's go ahead and look at v prime of 4. So we're looking at a sharp turn, and so we know that it doesn't exist. But the way to prove that is if you look over here, basically we're looking at it approaching from the left side and approaching from the right side. And since they're both linear functions, the limits are just going to be algebraic slopes. So here we have from the left side, at 4 it's 420, so 20 minus 0 over 4 minus 0, we get 5 is the ultimate answer. And from the positive side, we have a horizontal line, so that comes out to 0. And obviously 5 does not equal 0, so that's how we know that there is no differentiation possible at that point. Moving on to v of 20, I'll remind you again, it's a linear function. So at v of 20, we have, here's the algebraic slope, if you didn't know that, y2 minus y1 over x2 minus x1. So just plugging in numbers, 20 minus 0 over 16 minus 24, those are the points up here and down here of this line. It's the endpoints of the line. And so we get 20 over negative 8. Now we're simplifying to negative 5/2. And then the units. So if you remember in the part A I showed you those three graphs. So this is a velocity over time graph, and like I said in those graphs, the slope of a velocity over time is acceleration. And acceleration is always in distance per unit of time squared, and in this case we're given meters in seconds, so meters per second squared. And that's part B. Okay, moving on to part C now. So let A of t be the car's acceleration at time t in meters per second, or meters per second squared. For 0 is less than t is less than 24, write a piecewise defined function for A of t. So this is pretty straightforward. It's basically just asking us to break the slope down of this graph. And so the graph is pretty clearly delineated into 3 slopes, so we're going to break into the piecewise into 3 pieces. And luckily, since the slopes are all linear, it's just algebraic slopes again. So some of these we've already gone over. I'll just skim over it. Basically, you can look at the math. It all comes down to the points up here. And so basically from 0 to 4, we have a slope of 5, or an acceleration of 5. From 4 to 16, acceleration is 0. 16 to 24, we have an acceleration of negative 5 halves. That's right there. And the other two we can see earlier from up here. Oh, and then so just also tying into part B, we are using less than signs rather than less than or equal signs because these are both sharp turns, and as we just showed, there's no slopes at sharp turns, so we're using less than signs. Okay, lastly is part D. So find the average rate of change of v over the interval from 8 is less than or equal to t is less than or equal to 20. Does the mean value theorem guarantee a value of c for 8 is less than c is less than 20 such that v prime of c is equal to the average rate of change? Why or why not? Okay, so once again, just like everything else in this problem, we're actually just looking at algebraic slopes. So we have 8 comma 20 and we have 20 comma 10. The way we got the number 10 is, if you go back, we found out that the slope of this hypotenuse of the triangle here is negative 5 halves. So that basically it's just math. It comes out to 20 comma 10. So we're going to go to y2 minus y1 over x2 minus x1. We get 20 minus 10 over 8 minus 20. 10 over negative 12, which simplifies to negative 5.6 meters per second squared. It doesn't ask for that, but you should probably give it anyways. Once again, that's because the slope of a velocity over time is acceleration. And then coming into the mean value theorem, note the mean value theorem does not apply here, and that's because of this point here, 16 comma 20. Like we've stated in other parts, it's a sharp turn, and sharp turns are not differentiable, and the mean value theorem asks for the function to be continuous, which it is, and also differentiable across the entire region. So we have a continuous function, but we do not have a continuously differentiable function. And as a result, the mean value theorem does not apply, and we cannot guarantee that somewhere on this it'll equal negative 5.6. In fact, just by looking at it, you can tell that it does not. All right, so that's number 5.